In section 3, we are going to take a look at something called errors and then power. So what this section is answering is, how do we know we've chosen the correct significance level and that we have made the correct conclusion to either reject or fail to reject our null hypothesis? So we're going to start by looking at an example. So in a specific state, their DMV claims that 60% of teens pass their driving test on the first attempt. An investigative reporter examines an SRS of DMV records for 125 teens. 86 of them passed the test on their first try. Is there convincing evidence at the 0.05 significance level that the DMV's claim is incorrect? So for our null hypothesis, we are using the claim that the p is equal to 0.6. For alternative hypothesis, the wording here is, it doesn't specifically say whether or not we're looking to see if the proportion is bigger or smaller. We're just trying to see if the DMV's claim is incorrect. So this is an example of the alternative hypothesis being does not equal. Now I'm going to check my conditions. So we're going to start with random. And we did take an SRS, so we're good there. For independent, my sample size of 125 has to be less than or equal to 10% of all teens, which there's at least 1,200 of those, so we're good there. And then for normal, 125 times 0.60 has to be greater than or equal to 10, and 125 times 0.40 has to be greater than or equal to 10. And since half of 125 is 62.5, we've met those conditions. So now for my p hat, we know that 86 out of 125 passed the test on their first try, which is exactly 0.688. So if I have an exact value for p hat, I'm going to use it. So now for my z-score, we're going to do 0.688 minus 0.6 divided by our standard deviation, the square root of 0.6 times 0.4, all over 125. And in this case, it doesn't matter if I use the test on my calculator or my formula, because I don't have to round for my p hat. And if I don't round in my formula, I should get the same answer. So I'm going to plug this all into my calculator in one step. And we're going to get a z-score of 2.01. So now I'm going to go to normal CDF. So here's where it gets a little bit tricky, because if we're looking at a specifically less than or greater than situation, so a one-sided hypothesis test, I know where's my lower bound, where's my upper bound, because I have a less than or greater than. When it's a does not equal, what goes in for my lower bound and my upper bound is based completely on whether or not my z-score is positive or negative. So because my z-score is a positive 2, and that's above my mean, my lower bound is actually going to be my z-score. So my lower bound is going to be 2.01. My upper bound is going to be 1E99. We'll have a mean of 0 and a standard deviation of 1. Okay. And that is going to give us 0.0222. Now, here's another thing. Whenever my alternative hypothesis does not equal, I remember, if you think back to the last section, my p-value was the combined area of it being either above or below. So I actually have to multiply this value by 2 to get my p-value, which is going to give us 0.0444. So now when I compare my p-value to alpha, 0.0444 is less than my alpha of 0.05, which means we reject our null hypothesis, which means there is evidence to show the true proportion of teens who pass their driver's test is not 60%. Don't know what it is, but we're just going to say it's not 60%. It could be higher, it could be lower, we don't know. So we want to ask ourselves the question now, how do I know I chose the right alpha and that this was the correct decision? Because 0.0444 is pretty close to 0.05. So if I had chosen a smaller level of significance like 0.02, I would have had a different conclusion. I would have failed to reject my null hypothesis, which means there wouldn't have been enough evidence to show that the proportion isn't 60%. So that's what we're going to talk about now, are the types of errors. So we're going to kind of look at this through a table. So there are two types of error, a type 1 error and a type 2 error. So if your decision is to reject the null hypothesis, but you should have failed to reject, this is called a type 1 error. Now, obviously, if you reject the null hypothesis and you should have, you made the correct decision. And if you fail to reject the null hypothesis and you should have failed to reject, also the correct decision. But if you failed to reject the null hypothesis and you should have rejected, this is what we call a type 2 error. And we're going to go into more detail about what a type 1 and type 2 error are. So let's start with a type 1 error. So a type 1 error occurs when we reject the null hypothesis. So we had a low p-value when we should have failed to reject the null hypothesis. So when we set the significance level, which I'm just going to abbreviate, we are setting up our type 1 error. Our significance level determines what is considered a low enough p-value. So our alpha tells us what p-value is low enough. So when you're trying to figure out the probability that you make a type 1 error, that is equal to your alpha. So if your alpha is 0.05, that's the probability you're going to make a type 1 error, which is 5%. Okay? The p-value will tell us that it is still possible, but not probable. So even if I get a p-value less than alpha, it's still probable that it happens because it's not 0, but it's not necessarily, it's still possible it happens, but it's not necessarily probable because it's such a low probability. So what it's saying is we say that we have convincing evidence of our alternative, but we really don't. Kind of going along with the idea of a type 1 error is something called power. And when we are running a significance test, we want to try and see if we're able to reject the null hypothesis. The whole entire point of a significance test is to gather evidence against the null hypothesis. So when we do that correctly, it's a good thing. So we want to have a good significance test in order to reject the null hypothesis. And the probability that we do it correctly is called the power of a test. So power is the probability you have rejected the null hypothesis correctly. We are not going to be calculating this by hand, so don't really worry about it. All you have to know is what power is and what it represents. You don't have to know how to calculate it. So it is the probability we reject H naught correctly. Okay. And the higher the power, it is more likely to reject the null correctly. So higher power is good. Lower power is bad. But again, we're not going to talk about how to calculate it. You just have to know what it is. Okay. And then a type 2 error. So type 2 error occurs when we fail to reject the null hypothesis, which means our p-value was not low enough when we really should have rejected the null hypothesis. Now, they made up its own symbol to represent the probability of a type 2 error, and it's the Greek symbol beta. We're not really going to do anything with it because it's not really part of the significance test. They have a symbol for it. It's not like I'm going to say this is beta or anything in it. So just kind of review. The power is the probability that we rejected when we should have rejected. Type 2 is the probability that we failed to reject when we should have rejected. And then the probability you make a type 2 error is equal to beta. So because of the relationship that exists between power and type 2, that tells us that power is equal to 1 minus beta. Which again, I'm not really going to be giving you a beta, so it's not like we're actually going to be calculating power or the probability of a type 2 error, but it is the relationship that exists. So let's talk about interpreting these errors. So one thing you have to always ask yourself is, what type of error would you really want to have? Would you rather have? And it completely depends on the problem. Whether or not because one error is worse than than the other error depending on the problem. Because for some tests, we want a low type 1, but for others, we would want a low type 2. So let's kind of look at an example of this. So a medical doctor uses a diagnostics test to determine whether a patient has arthritis. And a treatment will be prescribed only if the doctor thinks the patient has arthritis. The hypotheses might be stated as follows. The null hypothesis, the patient does not have arthritis. The alternative hypothesis, the patient does have arthritis. So if we're thinking in terms of what a type 1 and type 2 error are in this setting and explain the consequences of each, that is something that you're going to have to be able to do. So we'll start with our type 1 error. So if you remember back, type 1 is rejecting when you should have failed to reject. So we say the patient has arthritis when they really don't. Okay. And then a consequence of this could be that the patient gets unnecessary treatment. Our type 2 error, which is failing to reject when you should have rejected, is you say the patient doesn't have arthritis, when they do. So a consequence of this is that the patient doesn't get the treatment they need. So in this situation, I would say a type 2 error is worse than a type 1 error, because I'd rather get treated for something unnecessarily and then later find out that I don't really have it versus not getting treatment for something I do have. So again, type 1 versus type 2 is very situationally based. So let's go ahead and we're gonna put all of the things that we've talked about together again in a table and talk about what affects our errors. So when we reject and we should have failed to reject, that is our type 1 error, which is denoted by alpha. And when we rejected and we should have rejected, that's our power, which is 1 minus beta. Failing to reject when you should have failed to reject doesn't really have anything. It's just, yay, we did it correctly. And then lastly, failing to reject when you should have rejected is our type 2 error, which is denoted by beta. So as we've kind of already previously discussed, we can set our type 1 error with our significance level. So the higher your type 1 error, the greater the power. And the reason that happens is the more likely we are to reject the null hypothesis, the more likely we are going to do it correctly. So the higher your alpha, the more likely you are to reject your null hypothesis, which means you're more likely to do it correctly. So the higher the alpha, the more likely we are to reject the null hypothesis correctly. But it also means we have a higher chance of rejecting when we shouldn't. So it actually also increases the probability of a type 2 error. It increases our likelihood of a type 1 error. So with the type 1 error increasing and the power increasing, what happens to our type 2 error? So the higher alpha is, the more likely we are to reject, which actually lowers the chances of us failing to reject altogether. So the higher the power, the lower the type 2 error is. So that tells us that significance level, type 1 error, and power all have a direct relationship, which means they increase or decrease by the same amount. And then type 2 has an indirect relationship with all of them, which means when the others increase or decrease, it does the opposite. And it's kind of better to kind of look at this in a picture. So if you increase alpha, you increase your type 1, and you increase your power, and you decrease your type 2. And if the opposite happens, you decrease your alpha, you decrease your type 1, you decrease your power, but you increase your type 2. So just nice to kind of put it all together in a little box. So that asks the question, what is the best alpha? Like, how do we make sure we're not likely to commit a type 1 or a type 2 error? And that is why we typically use an alpha of 0.05. It's kind of considered the best alpha to limit the chances of performing a type 1 or a type 2 error. So 0.05 is the most commonly used level of significance. And if it's not stated in a problem what your level of significance is, you should use 0.05. So let's look at one more example. So a drug manufacturer claims that less than 10% of patients who take its new drug for treating Alzheimer's disease will experience nausea. To test this claim, researchers conduct an experiment at the 5% significance level. So we're going to start off with describing our type 1 and type 2 error. So first, it's helpful if we know our null hypothesis and alternative hypothesis. So our null hypothesis is the proportion is 0.10. The alternative is their claim that it's actually less than 0.10. So for our type 1 error, we reject when we should have failed to reject. So you determine less than 10% of patients experience nausea when they really don't. And a consequence of this would be that the manufacturer won't do anything to fix the medicine. This isn't necessarily the only consequence. Another consequence would be that a doctor prescribes a medication that they think will help their patient's nausea, but it really doesn't. There's not necessarily one correct answer to consequence, but it should be something that does affect the results. And then for a type 2 error, that's when you fail to reject and you shouldn't have. So we determine that less than 10% of patients do not experience nausea when they do. So a consequence of this is that the manufacturer spends money and time to fix the drug unnecessarily. Which isn't necessarily a bad thing in terms of patients, because then maybe it would lower the percentage even more. So in this case, I would say a type 1 error is the worst of the errors to make, because the medication isn't really working and patients think it is. Whereas if you perform a type 2 error, you fix it, probably make it better, and it helps patients better in the long run. Right. Next, let's say hypothetically, the test has a power of 0.54 to detect the alternative is true. Explain what the power means in this setting. So that means the probability we find less than 10% experience nausea correctly is 0.54. Because remember, the power is the probability you rejected correctly. So the probability, if you reject, that means your alternative hypothesis would be true, kind of in quotes. So the probability that less than 10% experience nausea correctly is 0.54. So what's one way to increase the power in part B? So we kind of talked about this. If you want to increase power, you increase your significance level. So that would mean you're even more likely to find less than 10% experience nausea correctly. But it also makes you more likely to create a type 1 error. Okay. So based on these previous two examples, we know, in the wording of our problem, we know that the power of the test at the 5% significance level against the alternative is 0.54. We are going to decide to use alpha equals 0.01 instead of the 5% significance level. With no other changes, will the power increase or decrease? So you have to think back to the little table we made on the previous page and how decreasing our alpha affects our power. And they have a direct relationship, which means if we decrease significance, we decrease the power. So power will decrease when decreasing alpha since we are decreasing the probability we reject H naught completely. So remember, if we decrease alpha, we're more likely to create a type 2, more likely to perform a type 2 error, which is failing to reject when we should have rejected. So a lot goes into choosing a significance level, and unfortunately, no matter what we choose for a significance level, we can never know for sure if we've committed a type 1 or a type 2 error. We can't know, which is why it's very important that you choose your level of significance carefully. So that's why we always use 0.05, just to kind of, as I said before, kind of limit the probability or the chances that we've performed a type 1 or a type 2 error. So let me know if you have any questions about power, type 1 errors, or type 2 errors.